This is sections 10.6 and 10.7 of Honors Algebra 2, Applications of Logarithms. Some notation before we begin. Since it's so common in our decimal number system, our base 10 number system, we often write the log base 10 of x as simply the log of x. Thus, if no base is given for the log, it is assumed to be base 10. So here are two examples. Find y to three significant digits. Number 1, the log of y equals 0.8995. So that's really a log base 10 of y. So this is equivalent to saying the exponential equation 10 to the 0.8995 power equals y. So y is just going to be 10 to the 0.8995 power. And obviously, to do that, I'm going to use my calculator. So my calculator has a 10 to the x option right there above the log button. So all I have to do is click second log, and it will take 10 to a power, 0.8995. I could also just manually type 10 and use the caret key to get an exponent. So this is about 7.93. So y equals, or approximately equals, 7.93. That is three significant digits. Number 2, the log of y equals 2.4825. So again, 10 to the 2.4825 power is going to equal y. So y will be approximately 10 to the 2.4825 power. So about 303.74. I'll go ahead and write that with four significant digits, 303.7. Simple? Of course. This formula is called the change of base formula. It says the log base a of x equals the log base b of x divided by the log base b of a. So I can take any log and I can rewrite it with different bases. Why is this useful? Well, our calculators can compute logarithms with a base 10, but not with most other bases. So if I wanted to be able to do number 3 here, the log base 4 of 7, 7 is not a power of 4, so I couldn't really easily do this manually. I would need to do it on my calculator, but my calculator doesn't have an option for the log base 4. So instead, I need to tell it how to do this in terms of the log base 10, which my calculator does know how to do. So I would change the base on this. Changing the base means the log base 10 of 7, the thing I'm taking the log of, divided by the log base 10 of the original base, which is 4. So remember, if it's a base 10, I don't need to write the base. I can just write log of 7 over the log of 4. So that's what I'm going to tell my calculator. Let me pull up my calculator. I'm going to tell it to do the log, which is this button called log right there. The log of 7. Close the parentheses around that. Make sure you do that. And then divided by the log of 4. So that log button on your calculator is a base 10 log, and only a base 10 log. This is telling it to do the log of 7 divided by the log of 4, which is really the log base 4 of 7. So this is approximately 1.40. Notice it's approximate because this is actually an irrational number. So that means, of course, that 4 to the power of about 1.40 is 7. Number 4, solve 3 to the 2x equals 5. Okay, previously when we had equations like this, I could write both sides with the same base and then set the powers equal to each other. Well, I can't write 5 and 3 with the same base. So, instead, I'm going to convert this to a log. This has its equivalent log form of the log base 3 of 5 equals 2x. Those two equations are equivalent. One is the exponential form, the other is the log form. So if I'm solving this for x, x is going to be the log base 3 of 5, all divided by 2. Okay, well, the log base 3 of 5, I don't immediately know, so I'll do it on my calculator. So I'm going to have to do the log of 5 over the log of 3. So those are base 10 logs. And then I'll divide by 2. Remember, that is really just multiplying by 1/2. So, on my calculator, I'll do the log of 5, close the parentheses, divided by the log of 3, close the parentheses. That's about 1.4649. I will then divide that by the 2. So 0.732 approximately. So Mr. Shaver, when will I use this in real life? I hate that question, and you know it. Well, I have an answer. Many things in the real world, as if this class is not the real world, can be modeled by exponential functions. If the value of something is multiplied by a constant rate over each interval of time, then it has an exponential model. If something is going up by a constant multiple, it's an exponential model, or going down by a constant multiple. If that rate is greater than 1, it is called exponential growth. If that rate is between 0 and 1, it is called exponential decay. It's going down. Solving these models might require the use of logarithms. So what I've got for you now are some formulas, and we will practice these formulas through our classwork and warm-ups in class. So the first one is compound interest. A equals P times 1 plus R over N to the NT power, where A is the final amount, P is the principal amount, which is the beginning amount, what you start with. R is the annual interest rate, expressed as the decimal, so if it was 2%, you put in 0.02. N is the number of times per year that the compounding occurs, so if it compounds quarterly, N would be 4. If it compounds monthly, N would be 12. If it compounds daily, N would be 365. If it compounds just once a year, N would be 1. T is the number of years. This is like a bank account, which is compounding every certain period of time with a constant rate, where the rate is R. That's an exponential equation, because the variable, which is really t, because R and N are fixed and P is fixed, the variable is t, and it's in the exponent. So this is an exponential equation. Hopefully, if it's your money, it's exponential growth and not exponential decay. Doubling time. A equals P times 2 to the T over D power. Again, t is the variable, it's time. A and P are exactly what they were before. A is the amount after a certain period of time. P is the principal amount, the amount that you start with. D here is the amount of time that it takes to double the population. And a very useful thing called half-life. A equals P times 1/2 to the T over H power. Again, A is the amount after a certain period of time, the amount of time T has passed. P is the principal amount, the amount you start with. T is your variable of time. H here is the half-life, which is the amount of time that it takes for the substance to decay to half of its original amount. What has a half-life? Well, radioactive elements have half-lives, which is actually very, very important in our world today as we use nuclear energy. We need to know how long it's going to take for it to decay. So here are your immediate practice problems. Number 1, find the log of 4.6. Number 2, find x if the log of x equals 3.7135. Number 3, solve 2 to the 3x power equals 7, writing your answer using logs, and writing your answer as a decimal to 3 significant digits. And find, number 4, the log base 3 of 5, rounding it to 3 significant digits. And that is the end of sections 10.6 and 10.7.